Hey everyone, hope you are all doing amazing. I'm Hajra Mughal and welcome back to Physics Unlocked. So students, in our previous video, the part 2 of lecture series of dimensions, we have discussed the second advantage of dimensional analysis means to drive the possible formula, and in today's lecture we are going to discuss some terminologies used in dimensional analysis and the limitations of dimensional analysis. Students, there are few terms that are used in dimensional analysis which are dimensional variable. What is meant by dimensional variable? A quantity, a physical quantity which have the dimensions but variable magnitude, means that quantity can vary in magnitude but have dimensions as well. What are those quantities? For example, the force, we can measure force, yes, it has a dimension, yes, and the quantity, the magnitude of the force can vary, depends on the situation, that which kind of force we are going to measure and where we are going to measure that force. Same goes for energy, velocity, acceleration, power, and many more quantities. All those quantities have dimensions and they have variable magnitude. That's why they are known as dimensional variable. Okay, this is one more quantity that we can use in dimensional analysis, that is dimensional constant. Dimensional constant means those physical quantities they have dimensions but they are constant in magnitude. For example, the speed of light. We know that the speed of light having the same dimension as the speed and velocity, which is meter per second. It means the dimension of the speed of light will become L t minus 1. So, but the value of the speed of light is constant. So it has a dimension but the magnitude is constant. Same goes for Planck's constant. It has a value, fixed value. The magnitude doesn't vary. It has a fixed magnitude. So that's why it is known as constant, but it has dimension because it contains some unit, like the Planck's constant have unit joules into second. So the dimension of energy into second means T. So it has a dimension. Same goes for universal gas constant. The formula which we can use to find the dimension of G is F equals to G m1 m2 over r squared. So it has a dimension but it has a constant magnitude. So these quantities are known as dimensional constants. This is one more quantity, one more term that we usually use in dimensional analysis, that is dimensionless variable. What is meant by dimensionless variable? A physical quantity having no dimension but variable magnitude, means the magnitude varies but it has no dimension. Usually we see this kind of variable whenever we have a quantity that have the same fraction, means you can see the formula of a strain. The strain is the ratio of the change in dimension divided by the original dimension. For example, if we are looking strain in 3D, so the change in volume divided by original volume, so it is a dimensionless quantity but it is a variable quantity. Same goes for plane angle and solid angle. They are also dimensionless variable. One more term, dimensionless constant. It means the physical quantity is dimensionless and also a constant. For example, a pure numbers like 1, 2, 3, and the number, for example, pi. Pi is a dimensionless constant. It's a constant having no dimension. Limitations of dimensional analysis. So students, in our previous lecture, the part 2 of the lecture series of dimensional analysis, we have seen some advantages of dimensional analysis, or we can say the applications of dimensional analysis, in which we can use dimensional analysis to check the consistency of an equation, that the equation is dimensionally correct or not. And there was one more application, that was to drive the possible formula by using the dimensional analysis. But Students, there are some limitations of dimensional analysis, or you can say there are some drawbacks of the dimensional analysis, in which the first drawback or a limitation is that dimensional analysis cannot determine the dimensionless constant when driving a possible formula. Let's take an example. You must have studied the equation of motion, that S is equivalent to ut plus half at square. If I use dimensional analysis to check the consistency of this equation, then this equation is dimensionally correct. When I substitute the dimension of S over here, ut and at square, then this equation is dimensionally correct. 1 upon 2 is a dimensionless constant. So we do not put any dimension of 1 over 2 in the equation, because this 1 over 2 is a dimensionless constant. So if I write 1 over 4 here or any other number over here, even though that in the equation will be dimensionally correct. For example, if I write 1 over 4 here, so even though if I check the equation, the dimensions of the consistency of this equation, then this equation will be dimensionally correct. But this formula is wrong, because the dimensionless constant is 1 over 2 here. So this is the drawback of the dimensional analysis, that it does not determine or drive the constant entity. Like in our previous lecture, we have studied a formula of time period of simple pendulum. We have drive a complete formula of time period of simple pendulum, but the constant 2 pi was still unknown. We don't have any method in the dimensional analysis to find out the dimensionless constant. So let us see one more limitation. The dimensional analysis does not distinguish between the physical quantities having same dimensions. Let us see an example. The formula of work done is force into displacement. If I calculate the dimension of work done by substituting the dimension of force, which is mlt minus 2, and the displacement is L, the final dimension will be ml square t minus 2. And if I calculate the dimension of energy as well, the dimension will be the same, ml square t minus 2. So, and if I calculate the dimension of torque, then the dimension will be the same again, ml square t minus 2. So dimensional analysis does not distinguish between the physical quantities having the same dimensions. It will not tell you, if I know this dimension ml square t minus 2, it could be, it may be work, it may be energy, it may be torque. So we cannot distinguish in between the physical quantities by using this analysis. So this is one more drawback. Dimensional analysis cannot be used to drive a formula containing trigonometric functions, exponential functions, and log functions, because these functions are dimensionless. So we cannot drive a formula we cannot drive any equation that contains these functions. So this is one more drawback. Other drawback is the dimensional analysis doesn't always prove that the relation is physically correct, although the relation is dimensionally correct. What does it mean? Because an equation is dimensionally correct, that doesn't necessarily make it physically correct. For example, we know the Einstein's famous equation E is equivalent to mc square. This equation is dimensionally and physically correct, but if I write this equation as E is equivalent to 15 mc square, so it would be dimensionally correct, but this equation is wrong. So this is one more drawback. One more drawback is this analysis will not give you any information regarding whether the quantity is a scalar or a vector quantity. Scalar means those quantities having only magnitude, and vector means having magnitude plus direction. So this analysis will not give you information regarding any direction of the particular physical quantity. So what we have done up till now, we have seen some terminologies. There are 4 terminologies of dimensional analysis: dimensional variable, dimensional constant, dimensionless variable, dimensionless constant, and 5 limitations of dimensional analysis. Thanks for tuning in. If you like this video, be sure to hit that subscribe button and click the notification bell to stay updated on my latest uploads. I appreciate your support and can't wait to share more exciting content with you.